Okay. Thanks. Right. So welcome back to this second part of the afternoon. And we are going to start with Daniel Kious, who's going to talk about finding geodesics using reinforcement learning.
All right. Thank you very much for the invitation. Thank you to all the organizers. So I hope this will go well. Last night I dreamt I was giving this talk in person. So that was the good dream part, and the bad dream part was that I was giving it in French and realized only at the end that I was talking in French to an English-speaking audience. So I'll try not to do that today. All right. So this talk is about, as the title says, finding geodesics using reinforcement learning. And that's joint work with Cécile Maillet, who is in Bath as well, and Bruno Chapira, who is in Marseille. So the starting point is trying to understand this phenomenon according to which the ants find optimal paths from their nest to a source of food. So in this picture, you see actual ants starting here, they have food here, and they find somehow the shortest path from the nest to the food. Here there is some obstacles, so they cannot go straight. And they don't do any weird loop, they just go straight to the food. And the idea of some biologists is that they do that using pheromones, right? So they leave pheromones wherever they go, and following ants are going to smell the amount of pheromone on different paths, and they will be more likely to take paths where a lot of ants went before, right? So in real life, it looks like it's more complicated than that. There are other mechanisms, but we try to understand only this pheromone trail phenomenon. And there are other phenomena that correspond to the same kind. Here, this picture corresponds to a slime mold, so the physarum, who is like a mushroom, sort of mushroom, that can grow optimal networks between different sources of food. So here, it's not a nest and the source of food. Is the mushroom is everywhere, and you have food here, and the mushroom tries to get all the food through some optimal transport network. And it's based, some of the biologists explain that with models that look similar to what we can do with ants. There are a lot of things on that in the literature, in the biology literature or applied mathematics, but all the models we could find are deterministic and mean field. So deterministic, you know what it means, and mean field just means that you take the number of ants to infinity and you look at the differential equation that corresponds to that. So our idea was to define a probabilistic model in the goal to understand that. So we want our model to be probabilistic, as I said, and to be local or agent-based, right? So we want something microscopic. We want to look at ant by ant, a finite number of ants, right? At a finite time. And the general principle that we want to see coming could be described by these two sentences. So global learning from local interaction, or simply saying something like self-organization, right? So we want to define a few local rules, simple rules that the ants are going to follow, that not necessarily mean directly that you want to find shortest path, but by some kind of what may look like a magical trick, you can see the shortest path arising, right? And our idea was to use random walks and reinforcement. Okay, so not exactly reinforced random walks, as you will see, but really random walks and reinforcement. So reinforcement corresponds to the idea that the more you have pheromones, the more likely an ant is going to take a given path. And random walks, because that's how they explore the environment. So let me give you the basic model. So I'm going to define, so it's a bit of a heavy slide, sorry. I'm going to define a game on a finite graph, right? On this graph, you have two nodes that are distinguished, and the nest, where you have the ants go. So I will stick to the ant vocabulary, but now it's just probability, right? I'm not a biologist, obviously. So that's where the ants start. That's where the ants want to go. That's the food. And you do the following. So you fix your graph with your two vertices. You give you assign a weight to each edge of this finite graph. Okay, here we just choose the initial weight of each edge to be 1. 1 doesn't really matter, could be 10, could be 100, could be different weights. I don't think that changes a lot. And you play the following game. So assume you've played up to time n, you have weights wn of e for each edge. And what you're going to do, you're going to send an ant from n, let it walk on the network G, so this graph, with the weights wn. So I'm going to say in a second what I mean by that. So you let the ant walk up until the time it reaches the food, and then you stop it here, right? And you observe the trajectory. All right. So when I say the ant is going to walk on the network GWN, so G with the weights WN, I mean that at each step is going to jump through an edge with a probability proportional to the weight of that edge, right? So WN is really the conductance of the edge E, if you know what conductance is. So as I said, you observe the trace, or I should have said trajectory, not trace. You observe the trajectory, so all the information of what this ant has done. And according to some rule, you're going to update your weights for round n+1, okay? And as I say, according to some reinforcement rule that I didn't talk about yet, I'm going to define it later, all right? So that's the game we're going to play. And what we want to know is asymptotically, can you see one path or several paths that are geodesics along which almost all the ants will walk, right? So if you look at the amount of walk that go through a path, they will be concentrated with weight 1, right? All of them will be concentrated on one given path or collection of shortest paths. All right. So what can you choose as a reinforcement rule? Well, I will give you several possibilities. So the way we do it in general is that, okay, we observe the trajectory of the nth ant, and we're going to choose a path gamma n, all right, whose edges are a subset of the edges of the trajectory of the ant. And this path starts at n and ends up at f, right? So we just, within the trace of the ant, I choose one path from n to f. All right, and then I'm going to add 1 to all the edges along that path. All right, so again, I didn't say how I choose this path gamma n. Okay, so that's where you have several choices, and I'm going to give you three possibilities. You can come up with a billion different more, I guess, but here are the 3 that we considered. The first one is what we call the uniform geodesic ant process. Okay, so that's somehow the more efficient, but maybe the least relevant if you want your agents, your ants to have low rationality, right? So here you say the following. So imagine that your nth ant has done this trajectory, right? So you see the trace. Then you're going to look at the trace and find all the geodesics of this trace. So here I have 2. I have this one, right, that you can see here. And you have the other one, which is here, right, which I draw again here, right? And you're going to choose one of these geodesics with uniform probability. And you're going to reinforce the one you choose. So for example, 41.5, I'm going to reinforce this path. I'm going to add 1 only to the weights of those edges, all right? And as I said here, it corresponds to some kind of expert level hiker, right? You know where you have walked, and you're going to go back to your nest, leaving your pheromone because you're happy to have found food, and you're going to go back home using a geodesic path. So you're really an expert hiker. You know what's the shortest path within your trajectory, right? So that's one possibility, the uniform geodesic ant process. Another possibility, which is my favorite, is what we call the Loopy raised ant process. So in this one, you look at the whole trajectory of the ant. So here, for example, the ant does that stuff. And you're going to do the following. You're going to say, okay, the ant is going to go back to its nest. And every time it's at a crossroad, it's going to use the edge it first came from, right? So that's exactly what At least I would do if I was hiking, right? Every time I'm across the road, I would say, oh, where did I come from? I came from here, so I'm going to go back through that road, all right? So that's some sort of hiker with local memory, so you go back from where you first came from. And mathematically, it's just the loop erasure of the backward trajectory, right? So the ant is going to follow its trajectory backward, but it's going to avoid doing useless loops. It's going to do the loop erasure of its backward trajectory. All right. And as you can see here, so this guy is the loop erasure of the backward trajectory, and this guy is the geodesic, and these are clearly different in general, right? So this corresponds to a lower level of rationality for the ants. And that also corresponds to a model where the ants leave pheromone when they go back to their nest, right? Rather than leaving pheromone when they go to the food. And the last one is when they leave pheromone when they go to the food. So in that case, in the trace reinforcement process, you just leave pheromone all over the place and you reinforce the whole trace. All right, so if the ant has gone there, then you reinforce everything, you add weight, you add 1 to the weights of all those edges. All right. So now in 12 minutes, what I want to tell you essentially is that, so this defines more a class of models than a model, right? And what I want to emphasize here is that changing these these details about the updating rules is going to change a lot what your model is going to do in the end, right? And different rules are more efficient or less efficient than others, all right? So what are the conjectures that we have? So that's with Cécile and Bruno. So we think that on any finite graph with 2 distinguished vertices, right, a nest and a source of food, well, the asymptotic weight, so that recall that Wn is the weight of edge E after the nth round, right? So Wn of E divided by n converges almost surely to some Ki, right, which is a random variable. And this Ki is going to be different according to the different updating rules. So let me be more precise. So we think that the loop erased end process, right? So when you're on my level of hiking, when you go back through the loop erasure, we believe that an edge will survive, okay? We'll have a positive density of ants asymptotically, a positive density of ants, if and only if it's on a geodesic, right? So if it survives, then it's along a shortest path. And if you see a shortest path, then edges along that path will survive, right? So that's what we believe. Whereas for the uniform geodesic, so where you choose directly a geodesic when you go back home, we think that if an edge survives, then it's along a geodesic, but not the other way around. Okay, so you may have geodesics that don't survive. And for the trace reinforced end process, it's a bit unclear what happens, but what we can say is that the limits are suboptimal in a way that I'm going to explain in a second. All right. So that's the conjectures. So now what did we prove? Well, we proved some of it. Our main result, I would say, is about series parallel graphs, right? So we proved the first items, the conjecture about the loop erased end process on series parallel graphs. So I'm going to tell you what are series parallel graphs. So what we would like, obviously, is to prove it on Z2, but we didn't do it yet. So series parallel graphs are graphs that are constructed or can be constructed recursively, right? So here I just wrote a recursive definition for it. So you start from a single edge with there's always 2 distinguished vertices for series parallel graphs. So you start with one edge with its 2 endpoints, and you say that this guy is a series parallel graph. Good, that's the base case. And then you can construct recursively series parallel graph according to 2 possible rules, 2 and 3. So in 2, I say you can take 2 series parallel graphs and combine them in series. Okay, so merge F1 with N2 here. And what you obtain is still a series parallel graph, right? And similarly, you can take two series parallel graphs and merge them in parallel. So you merge N1 and N2, and you merge F1 and F2. And what you obtain is still a series parallel graph. Okay, so you can construct like that recursively the whole class of series parallel graphs. And here's an example of one. So there is some kind of branching flavor to it. It's close to a tree in spirit, but it's not a tree, obviously, because you can see that there can be plenty of loops, right? What's forbidden is to have an edge from here to here, for example. That would kill the series parallel property, for example. All right. So theorem on that class of graphs, so on series parallel graphs with two distinguished vertices N and F, the loopy raised end process converges, okay? So all the weights, all the normalized weights of the edges converges, and the asymptotic weights are non-zero if and only if the edge is on a geodesic. Okay, so that's the conjecture I explained before, but on series parallel graphs. All right, so in short, the loopy raised end process finds all the geodesic. Okay, if you have a geodesic, it will find it in the sense that this geodesic will have a positive density asymptotically. And the only thing that survive are geodesics. All right. So that's the theorem one. Natural next question is, what about non-series parallel graphs? Well, that's much more, at least for now, much more difficult to tackle. And well, what we did mostly is just to study one simple example of graph which is not series parallel. So this guy. Okay, so I learned last week that it's not the right way to spell losange in English, but let's say it's French. And so we have this simple bridged losange. And we proved that, okay, the two paths that survive are the left path and the right path, and that they both survive with positive density, right? And the edge in the middle here that would create longer trajectories dies out. Okay, so this edge in the middle dies out and all the others survive, right? So it was just in order to prove the conjecture in a non-series parallel setting. All right. Oh yeah, what we proved as well is that in general, the uniform geodesic end process does not find all the geodesic. So if you take a graph that looks like that, okay, so you have a path of length L here, another path of length L here, same length, and whoop, just an edge. Then on that graph, well, this is a geodesic, this is a geodesic. You should think, okay, they should both survive, but actually we prove that for the uniform geodesic end process, one of them dies out with positive probability. All right, so that's the proof that the uniform geodesic end process does not find all geodesic. Okay, so we still believe it only finds geodesics, but not all of them. All right, so depending on what you want to do, could be good, could be less good than the loopy erasure end process. All right. So I think, yes, for the trace reinforced end process, it's less clear what you would obtain as a limit, but what we can prove, and what we proved, is that the limit seems to be deterministic. So here I say seems to be deterministic for reduced graph, and what I mean is that you don't want multiple edges close to F, close to the source of food, simply because these guys would have random weights, okay? Because I mean they will have random weights, but if you forget this case, if you assume that all the edges connected to F are simple, then it looks like the limit is deterministic and correspond to some fixed point of the dynamic. All right, so here I've put some examples. So, oh yeah, and here you can see that the middle edge, for example, in the bridge losange doesn't die out, right? So you don't find a geodesic in that case. Here, okay, you find a geodesic, but that's a very simple case. Here I have two paths of different length, and both survive almost surely. So again, even in a simple case where you have one path and the longer path, the uniform geodesic does not find the shortest path. It just let both paths survive. And you can even do some more stupid stuff like here, where you have the shortest path that is here, obviously. This guy will take all the ends, but some ends will keep on looping around like that in a useless way. Okay, so these are all examples that the trace reinforce and process is suboptimal, right, in terms of finding shortest paths. All right, so in 3 minutes, I will try to explain to you the basic mechanism of why it works, why this mechanism throw you back the shortest path. All right, so the idea is to see this model as embedded polyarn. So I'm going to give you 2 very simple examples that will show you why it works, okay? And the general proof is more complicated, obviously, but that's I think, the core of the idea. Right, so if you take this graph, for example, okay, so here I have opened the graph, right? So this corresponds only to that graph, right? But I just open it for clarity. You have the edge on the left, edge on the right. They are both geodesics. So what you want to see is both of them having positive weight asymptotically if you consider, for example, the loopy raised end process, right? And the probability that an ant starting from n goes through the left path is precisely equal to the weight of the left path divided by the sum of the 2 weights, which is here n plus 2, because I start with weight 1 and add weight 1 to one of them at each time step, each round. And that's also 1 minus the weight of the right edge divided by n plus 2. So if you know what's polyarn, you easily recognize that corresponds to the dynamic of a polyarn, right? And it's very well known that in that case, if you normalize the weights of the left edge and of the right edge, okay, which correspond to, let's say, red ball and green balls, you obtain in the limit u1 minus u, where u is a uniform random variable in 0, 1, right? So in particular, both colors survive, both edges have positive density asymptotically, right? So that's the case where you have two geodesics, right? And what happens when you have one geodesic and one longer path, right? So here I'm giving you the geodesic here, length 1, and a non-geodesic of a path of length 2 on the right, right? So there are 2 facts, is that the weight of the H2 is equal to the weight of H3 if you consider, for example, the loopy raised end process, okay? It works also for the uniform geodesic. Because, well, what you reinforce is a simple path from F to N, so you reinforce either that or that, okay? Therefore, the weight of 2 is the weight of 3, okay? They're equal as the first line. And if you add the weight of 1 and the weight of 3, you obtain N plus 2, because at each time step, you reinforce either this guy or these 2 guys. All right. And now if you know a little bit about random walks, you can very easily compute the probability to start from N and hit F through the left edge before hitting it through the right edge. And that's equal to the weight of the left edge divided by weight of the left edge plus 1/2 of Wn of 3, so the weight of this guy. And the 1/2 comes from the fact that here you have length 2. All right, so this divides your conductance by 2 somehow. And now, well, it still corresponds to some kind of polyarn, but it's a polyarn that has the following dynamic. When you pick up a red ball, you add 1 red ball, and when you pick up a green ball, you add only a 1/2 green ball. So it's an unfair urn, right? And in that case, it's again well known that Wn of 1, so the red balls have a proportion that converges to 1 almost surely, and Wn of 2, and therefore Wn of 3 divided by n converges to 0 almost surely. Okay, so the left path has density 1 asymptotically, and the right path has density 0 asymptotically. All right, and that's the basic mechanism why it works. So I'm not going to enter the details on how we generalize this idea in the case of series parallel graph, but yeah, I will stop here and I will just jump to the last slide with the end picture. Thank you.
Okay, thank you very much, Daniel. So are there any questions? Yes, Pascal?
Yes. So you said before the series parallel graphs, they are kind of like trees. Can you expand on that? And in particular, what came to my mind when I saw the picture was the loop trees of Curie and Korachemsky. Is there a relation?
Oh, I don't know the loop trees of Curie and Korachemsky. So
it's a way to construct a graph from trees by putting in loops in between corners.
I think it's very different.
Well,
sorry, can I jump in?
Sure.
Yeah. I think it's very different because for us it's really, we don't have, I think in their stuff it's a topology, I mean, it's a metric thing, right? I mean, the size of the loops is important, something, whereas for us all edges have length 1 or something. I mean, I think it's very different.
Mm-hmm. But is there any construction that relates a series parallel graph to a tree in some natural way?
No. I don't know. Cecile would know more than me, but I mean, my remark was just, I think why I feel like that is because of the recursive nature of the class of series parallel graph. Right? Okay. So trees are series parallel graphs, right? So you have an inclusion. I don't know. To me, there is a kind of similar flavor to it, but they are not trees, obviously, right? But I think this is the recursive thing that gives it a similar flavor somehow.
Okay.
There's a question from Matthew.
Yeah. So do you have any intuition for why the leap finds all the geodesics but the U gap doesn't?
No. No, I'm not sure. I mean, yeah. I mean, we have more than intuition in principle because we have a proof in a simple case, right? That doesn't happen, right? Mm-hmm. So I think it's a question of, I mean, in all these cases, you have and the same for polar-Ernst, right? You have a dynamic, some kind of dynamical system that have to obey like a general drift and a fixed point equation. And turns out, I'm not sure why, turns out that the fixed point equation for the uniform geodesic pushes you to equilibria where you have only, for example, in the simple case, only one of the geodesic surviving, right? And I think that the case where both survive is also an equilibrium that you can achieve with positive probability, but I'm not sure. But yeah, it creates some kind of like convex stuff, you know, in your landscape. So you are attracted by the equilibrium where you have only one geodesic surviving. So that you can see it in the computations, right? You can see it in directly in the dynamical system that you have this fixed point equation that pushes you to this equilibrium. But honestly, I don't have really a more intuitive reason for it.
Thanks.
Okay, so I mean, I could ask if you are sure that ants really have 3 segments in their body in addition to the head, but
I have no idea.
So I think we can all unmute ourselves and thank Daniel for a wonderful talk.
Yes.
And
let's head back.
No, I think now we have